Friends, welcome to the tutorial series on network analysis made simple. During the previous 4 tutorials on Laplace transforms, we learned the introduction to Laplace transforms in the first. In the next 3 tutorials on Laplace transforms of special signal waveforms, we discussed step functions, ramp functions, and unit functions. In fact, I feel these tutorials form the prerequisites to understand the present tutorial on impulse functions. Friends, impulse in general can be considered to be an event like lightning, flash or sparkle which occurs at a spur of a moment involving enormous energy. This you know it. So friends, during this travel, I will take you through from the known to unknown. First, we shall see what do we mean by impulse in brief, define impulse, and then proceed to the impulse in electrical networks. Friends, the concept of an impulse is an interesting phenomenon. Hope the discussion will be lively and interesting. Friends, on the lighter side, impulse is said to be something that causes something to happen at some instant of time. Is it not funny? But friends, impulse is related to every moving body having some mass and moving with some velocity. Such all moving bodies are said to have what is called as momentum. Friends, momentum in physics terms is defined as the product of mass into change in velocity. Its unit is say kg meter per second. But impulse is defined as the product of force into time for which the force is applied. Its unit is Newton second. We shall study the concept of impulse as we proceed further. But before that, let me illustrate a few events that produce impulse. Consider an event when the bowler in a cricket match bowls. The ball travels with some velocity towards the batsman. The ball has some mass. So, when it is moving with some velocity, it is said to have some momentum. But when the batsman hits the ball, it moves away from the batsman with different velocity. So, the momentum of the ball changes. Hence, this change in momentum is an effect of impulse. Friends, let me illustrate another interesting event. You see that the car hits the wall with some velocity. Before it hits, it has some momentum. You observe that the direction of the movement of the car is reversed after hitting. The velocity also changes and the car comes to rest after some time. So, there is a change in momentum and hence this also is an effect of impulse. But friends, impulse in electrical network is different. The parameters that change with time are different. But the same concept can be extended to study the impulse in electrical networks. It's easy and very interesting, friends. Let's go ahead. Friends, as expressed earlier, a moving ball with some mass and velocity is considered to have some momentum. We know from the physics that force is equal to mass into acceleration or deceleration. But acceleration or deceleration is equal to delta V divided by delta T, that you know, where delta V is the change in velocity and delta T is the change in time. Let T be the change in time, then we can write force F is equal to mass into acceleration, and that is equal to mass into delta V divided by T, or F into T is equal to m into delta V, where m into delta V is the change in momentum in kg meter per second and F into T is known as the impulse in Newton seconds. So, impulse can be defined as the change in momentum. Hope you have understood it. Friends, also note that the change in momentum of the body and the impulse are equal to each other. Remember this. Friends, to emphasize the concept, consider any event of a car dashing onto a strong, sturdy and immovable wall. Let the mass of the car m is equal to 1000 kg and let the car be moving with a velocity of 36 km per hour. So, the car velocity in meter per second is equal to 36 into 1000 divided by 60 into 60, which will be V is equal to 10 meter per second. Now, let us find the force exerted by the wall on the car. Friends, you may now be thinking by recalling the previous event of bowling and the batsman hitting the ball. When the batsman hits the ball, force is produced by hitting. But here is an unmovable wall. How can it produce force? Friends, because of the heavy mass of the wall, indirectly the wall exerts force on the car. Well, we shall find the force produced by the wall. Number 1, when the car comes back to rest in 10 milliseconds after it just touches the wall, and 2, if the car comes to rest, say, only in 1 millisecond, V initial is equal to 10 meter per second, final velocity V final is equal to 0. So, delta V is equal to V final minus V initial, which will give us minus 10 meter per second. Change in velocity is negative because it is retardation. This you know. Similarly, initial time when just the car touches the wall, t initial is equal to 0. Final time when the car comes to rest, t final is equal to 10 milliseconds. So, the change in time t is equal to t final minus t initial, which will give us 10 milliseconds. Now friends, we know all the parameters required to find the change in momentum and the force exerted by the wall. Change in momentum is equal to m into delta V, and that is equal to 1000 kg into 10 milliseconds, which will give us 10 to the power of 4 kg meter per second. But we know F into T is equal to m into delta V. So, F is equal to m into delta V divided by T, and that is equal to 10 to the power of 4 divided by 10 into 10 to the power of minus 3, which will give us 10 to the power of 6 newtons. Similarly, consider the second case when t is equal to 1 millisecond. F is equal to 10 to the power of 4 divided by 1 into 10 to the power of minus 3, which will give us 10 to the power of 7 newtons. Friends, observe that the mass of the car and the velocity being same, or change in momentum being same, as time t reduces, the force exerted will increase. Hope you understand this. Friends, now if we extrapolate this, we see that as t tends to 0, f tends to infinity. Friends, this is exactly the concept of impulse. We shall extend this concept to impulse in electrical networks. Remember, as t tends to 0, force tends to infinity. Friends, next we shall go through the concept of a modified ramp. If you remember, we have already discussed this in the previous tutorial titled Unit Functions. Anyway, let me revise for your benefit here. Consider the modified ramp shown in figure. It is 0 for t less than t1 and it is 1 for t greater than t2. But it is a ramp of 1 by a units between time t1 to t2. Hence, it can be represented as f of t is equal to 1 divided by a into t for t between t1 to t2. Let us differentiate this modified ramp function. You observe that d by dt of f of t is 0 for t less than t1 as f of t itself is 0 during this interval. Also, d by dt of f of t is 0 for t greater than t2 as f of t is constant equal to 1 unit for t greater than t2. But between the time t1 and t2, f of t is equal to 1 by a into t. So, d by dt of f of t during this interval between t1 and t2 is 1 divided by a. Hence, we find that differentiating the modified ramp results in a rectangular function. If we find the area of this rect of t, we get area A is equal to base into height. Base is A units and the strength is 1 by A units. Hence, area A is equal to A into 1 divided by A, which will give us 1 unit, which means this function is a unit rectangular function. We shall use this unit rectangular function to obtain the impulse function. Consider an unit rectangular function shown in figure. It has a pulse width of a seconds. Let a is equal to t2 minus t1 and that is equal to t seconds. It has a pulse strength of 1 by a units. So, area A is equal to A into 1 divided by A, which will give us 1 unit. We observe that this unit rectangular pulse occurs at t is equal to t1. Note that. Now, let us go on reducing the pulse width and see what happens. If the time period t is reduced to half as shown in figure, the strength of the function doubles. Further, if the period t is reduced by 4 times as shown in figure, the strength of the function increases 4 times. Now, if we extrapolate as in the event of a car dashing, we get as t tends to 0, the strength of the function tends to infinity. The function obtained as t tends to 0 is a sudden spike of infinite strength and is known as impulse function. Observe that it occurs at t is equal to t1. Also, it is an unit impulse. If the unit impulse occurs at t is equal to 0, it is represented as delta t. Now, this function shown in figure occurs at t is equal to t1, so it is represented as delta t minus t1. Hence, it can be called as a delayed unit impulse function which occurs at t is equal to t1 seconds. Hope you have understood it. Friends, now we shall learn to identify and illustrate the given impulse functions. Two functions are shown in figure. One function is delta t. Observe that it is an impulse function which occurs at t is equal to 0 and is an unit impulse function. Its mathematical model is f of t is equal to infinity for t is equal to 0, which is undefined, and is equal to 0 for t not equal to 0. So, this unit impulse function can be defined as a function whose strength is 0 elsewhere other than t is equal to 0. It is an infinitely narrow spike with infinite strength but integrates to a value 1. Note that. Similarly, another function is 4 delta t minus 5. It is an impulse function which occurs at t is equal to 5 seconds and it has 4 times strength of unit impulse function. It is a delayed impulse function. Its mathematical model is f of t is equal to infinity for t is equal to 5 seconds, which is undefined, and is equal to 0 for t not equal to 5 seconds. So, this function can be defined as a function whose strength is 0 elsewhere other than t is equal to 5 seconds. It is an infinitely narrow spike with infinite strength, but it integrates to a value 4 as it has strength of 4 times the unit impulse function. Hope you got it. Next, we shall see an interesting fact that the differentiation of a step function transforms into an impulse function. This is another way of understanding the impulse function. Consider a modified ramp pulse of pulse width a seconds as shown in figure. This function is a unit modified ramp between time t1 to t2 as it has a strength of 1 by a into a, which is equal to 1 unit. If the pulse width a is reduced continuously as shown in figure, you observe that the unit ramp transforms into a unit step function as a tends to 0. But we know through our earlier discussion, the differentiation of a modified ramp transforms into a unit rectangular function, and as pulse width tends to 0, it transforms into an impulse. Is that right? Now, according to the figures shown, the differentiation of a unit step also should result into an impulse. How interesting is it? Yes, friends. The differentiation of unit step function results in unit impulse function. Hence, according to this concept, d by dt of u of t minus t1 is equal to delta t minus t1, and delta t minus t1 is equal to infinity for t is equal to t1, which is undefined, and is equal to 0 other than t is not equal to t1. This impulse function occurs at t is equal to t1, so it is a delayed impulse function. Hence, in general, we can say that d by dt of u of t is equal to delta t. Friends, to emphasize the concepts we have learnt, let us solve few problems. First, we shall find the Laplace transform of an impulse function delta t shown in figure. It is an unit impulse function which occurs at t is equal to 0. We know that the differentiation of a step function results in impulse function. So, L of delta t is equal to L of d by dt of u of t, and that is equal to S into L of u of t. You know that d by dt can be replaced by S. So, L of delta t is equal to S into 1 by S, which will give us 1. Next, we shall find the Laplace transform of the two functions shown in figure. The first function is 2 delta t, which occurs at t is equal to 0. We know that L of delta t is equal to L of d by dt of u of t, or L of 2 delta t is equal to f of s is equal to 2 times L of d by dt of u of t, and that is equal to 2 into s into 1 by s, which will give us 2. Similarly, L of 4 delta t minus 5 is equal to f of s and is equal to 4 into L of d by dt of u of t minus 5, and that is equal to 4 into s into e to the power of minus 5s by s, and hence L of 4 delta t minus 5 is equal to 4 into e to the power of minus 5s. Friends, we shall solve another interesting problem. Given y dash of t plus y of t is equal to delta t minus 1, let us find y of s. By taking the Laplace transform of the entire function given, we get L of y dash of t plus L of y of t is equal to L of delta t minus 1. But we know L of delta t minus 1 is equal to e to the power of minus s, and L of y of t is equal to y of s. Also, L of y dash of t is equal to s into y of s minus y of 0. We know y of 0 is equal to 2, which is given. So, L of y dash of t is equal to s into y of s minus 2. By substituting the value obtained, we get s into y of s minus 2 plus y of s is equal to e to the power of minus s. By rearranging it, we get s into y of s plus y of s is equal to e to the power of minus s plus 2, or y of s into bracket s plus 1 is equal to e to the power of minus s plus 2. So, y of s is equal to e to the power of minus s divided by s plus 1 plus 2 divided by s plus 1. Is it not simple, friends? Finally, let me conclude saying that an impulse function is an interesting concept. Its strength is infinite at the instant of time where it occurs. The unit impulse which occurs at t is equal to 0 is represented as delta t, and Laplace transform of delta t is equal to 1. The impulse may occur at any time in t. Say, if it occurs at t is equal to a seconds, then it is represented as delta of t minus a. And its Laplace transform is L of delta t minus a is equal to e to the power of minus as. The strength of an impulse may be multiple times the strength of the unit impulse. Also, we saw that the differentiation of a step function results in impulse function. Hope the concept of an impulse created interest to know more about it, friends. If this tutorial has ignited some of your thoughts, please send your feedback and suggestions to my email. Thank you for watching this video.